my name is Asmizaidah alias. Welcome to this simulation lab on investigating the state of matter. Today we will explore how temperature and pressure affect the pace of different substances using PET, state of matter, using basic simulation. For today's objective, we have three objectives, which is 1. To observe and analyze the different state of matter. Second, to understand the phase transitions such as melting, freezing, and evaporation. Third, to explore how temperature and pressure influence make using simulation tools. What is matter? Matter is state of matter refers to the physical form that a substance takes based on the arrangement and movement of its particles. The three common states of matter is solid, liquid, and gas. According to kinetic molecule theories, all particles are in constant motion. When we apply heat, they move faster and spread apart, causing phase transition. As seen in this heating curve, the substance melt at their melting point and boil at their boiling point. Intermolecular force play a key role in determining this transition temperature. Based on our hypothesis, if temperature increase, solid will melt into liquid, and liquid will evaporate into gases. While if pressure increase, gases may condense into liquid by reducing particle movement. Now, let's conduct our experiment using PET simulation. You can access this tool at the link shown at the screen.
So now, let's take a look at our simulation tool for today. As you can see, at the right top of the screen, we have different substances that we can select, which are atoms like neon and argon and molecules like oxygen and water. Here we have different states of matter in solid, liquid, and gas form. Then we can change the molecules to decrease or increase their energy, like we can heat the matter or we can cool it down. And here we have temperature control that we can choose whether we want it to be in Kelvin or in Celsius. As you can see here, in solids, molecules are tightly packed and vibrate in place. This gives solids their fixed shape and volume. In liquids, molecules are more spread out and can move around each other. Liquids have a fixed volume but can change shape to fit their container. In gases, molecules are far apart and move freely. This allows gases to expand and fill any space. These basic states of matter are essential to understanding how substances behave. Adjusting temperature and pressure can alter these states. So now I will drive you more on our today's experiment, and we will be exploring the phase changes of all the substances using these interactive simulations. We will observe how temperature and pressure influence the state of matter and see the substances transition between solid, liquid, and gas. Let's take a look at our setup. On the right, we have panel where we can select different atoms and molecules. Right now, we have chosen neon. At the top, we have pressure gauge, currently reading 0.0 atmosphere. There is also a thermometer, which is currently set to minus 259 Celsius, which is extremely cold. Inside the container, we can see neon molecules appearing as small cyan-colored circles. So let's observe how temperature influences the substances transitions. For instance, as you can see here, at At minus 259 Celsius, neon is in a solid state. We can see the molecules closely packed together, vibrating slightly but not moving freely. This confirms that neon is frozen at this extremely low temperature. Why this happens? This happens because at very low temperatures, the kinetic energy of the molecules is very low, so they do not move around freely. The weak intermolecular forces hold them in a rigid structured form. Now, let's increase the temperature using the heat control at the bottom. As we heat the system, watch how the molecules start moving more. At around minus 248 Celsius, something interesting happens, which is neon starts to melt. The molecules break free from their fixed positions but remain relatively close together, forming a liquid. This means neon has transitioned from solid to liquid. Why this happens? This is because as we add heat, the molecules absorb energy, causing them to vibrate more strongly. Once the temperature reaches the melting point, the solid structure breaks down and the molecules can move more freely. Now, let's increase the temperature even further. We can see the molecules moving faster and faster. At minus 246, around that degree, neon starts to boil and turn into a gas. Now, molecules are spaced out, moving rapidly in all directions. This phase change happens because at the boiling point, the molecules have gained enough energy to completely overcome intermolecular forces. As a result, they escape into the gas phase where they move freely in all directions. Now, let's cool neon back down. Watch as the molecules start slowly and slowing down and moving closer together. At around minus 246 Celsius, neon condenses back into a liquid. The molecules lose energy and start clustering together again. As we continue cooling around minus 248 degrees Celsius, neon completely freezes into a solid. The molecules stop moving freely and arrange themselves into a fixed pattern again. This shows how phase changes are reversibly and depend entirely on temperature and energy transfer. So, here's a summary of the phase transitions we observed for each substances. For neon, transitions between phases at extremely low temperatures due to weak intermolecular forces. It changes from solid to liquid below minus 248 Celsius and from liquid to gas above minus 246 Celsius. And for argon, it requires slightly higher temperatures than neon to transition between phases because of stronger forces. It melts below minus 189 Celsius and boils above minus 185 Celsius. And for the oxygen, it has a wider liquid range and moderate intermolecular forces. It melts below minus 219 Celsius, stays liquid between minus 219 Celsius and minus 183 Celsius and boils above minus 183 Celsius. And lastly, for the water, it requires the highest temperatures due to strong hydrogen bonds. Water melts at 0 Celsius boils at 100 Celsius and remain gas above 100 Celsius. So now let's explore how pressure affects phase changes. We will start by observing oxygen in its gaseous state at normal atmospheric pressure. As we gradually increase the pressure, notice how the molecules are forced closer together. This compression reduces their movement and the gas begins to condense into a liquid. As pressure increases, the particles of oxygen move more slowly and the gas transitions into a liquid state. This shows that applying pressure can cause gases to condense by reducing the kinetic energy of the molecules. Here is a summary of how pressure affects phase transitions for the substances we observed. As for the neon, even with the increased pressure, neon will remain in the gaseous state due to its very weak intermolecular forces. The pressure is not enough to bring its particles close enough for condensation to occur. And for the argon, with argon, we see it transition from a gas to a liquid at higher pressures. This is because its intermolecular forces are stronger than neon's, allowing it to condense into a liquid when the pressure increases. And for the oxygen and for the water undergoes condensation from gas to liquid under moderate pressure. Water's hydrogen bonding forces are what. And as for the water undergoes condensation from gas to liquid under moderate pressure. Water hydrogen bonding forces are strong enough to cause it. Apa ni? Water's hydrogen bonding forces. And as for the water undergoes condensation from gas to liquid under moderate pressure. Water's hydrogen bonding forces are strong enough to cause this phase change at a higher pressure than neon and the argon. And it is still easier to compress compared to gases with weaker intermolecular forces. So what do we gain and what are the advantages of this simulation video? This simulation offers several advantages, which are it is safe, interactive, and effectively visualize complex concepts. Through it, we gain valuable insights, such as how heat increases molecular motion, leading to phase changes. We also observe how cooling slows down particles, turning gases into liquids and liquids into solids. Additionally, we learned that different substances have unique phase change temperatures, depending our understanding of matter's behavior in various states. This hands-on approach enhances both learning and retention of these core scientific principles. And that is all for our simulation today. Thank you so much for watching.